Hi, everybody. So, I kind of disagree with how the structure of the book goes from here. There are certain things I want to do in a different order. So, I'm jumping ahead a little bit to closed sets. I think this is actually section 17. We're not going to do all of that, but in order to really define subspaces in the right way, I think, I want to do closed sets and a little bit of continuity first. So, apologies, but I'm going to go do this anyway. So what is a closed set? So we've defined open sets as these things that determine a topology on a set. So we'll say, given a topological space, let this be a topological space. Definition, a subset is closed if its complement is open. Closed if its complement, so that is the set X minus A, is open. Right, and of course, I guess we're using pink. That means X minus A is in tau. So you'll notice some things that being an open or closed are not necessarily like an either or thing. You can have sets that are open and closed. There's a really, really shitty meme that I'll have to send you guys to. I don't know, I think it's like 10 years ago now, from the birth of YouTube about this. So let's go through some examples. Examples are the best way to learn. So if I have the reals with the standard topology, so usually if I don't specify the topology, I mean the standard topology on the reals, then closed intervals are closed. In the standard topology. Why? Well, the complement is going to be equal to all reals strictly less than A, union all reals strictly greater than B. And both of those are open, using the definition of the order topology. Or you can just, use the basis. Let's say if I have, so we've defined open balls in R2 before. So let's say an open ball in R2 is of radius epsilon. Open ball of radius epsilon greater than 0 at P, so centered at some point P in R2, or we can even do Rn. This consists of all points in R2 such that the distance between P and Q is less than epsilon. So we define distance here to be norm of the difference. So this is an open ball. And so we would also associate a closed ball with this notation, with a little bar over it. So this would consist of all points, say, Q in R2, such that the distance from P to Q is less than or equal to epsilon. So it adds in the boundary. If I think about that, that's the ball. So the open ball is the interior. All the points strictly less than distance r, or epsilon. Probably should have made the thing a little bit bigger. What the fuck? What? That was weird. I don't know what just happened there. Let's say, well, we'll use the line. This is epsilon, this is p, and the boundary here would be some point q where the distance from p to q is exactly epsilon. Sometimes notability just kind of does weird little shit like that. So this is open, or sorry, this is a closed set. This is the closed ball. So to prove that, you have to prove that its complement is open. So, you take some point, let's say R in R2 minus the closed ball. So that means, in particular, if it's not in the closed ball, it means the distance from P to R is strictly greater than epsilon. And if it's strictly greater than epsilon, I can find some smaller little ball that's completely contained inside the complement. Say you take the distance from P to R and divide it by like 2 or 3, for example. We'll call this distance delta. Then the open ball radius delta, centered at the point R, will be completely contained inside the complement. And so therefore the closed ball is closed. Why do we care about these things? Well, one thing that's pretty important is that you can phrase the definition of a topological space or a topology completely in terms of closed sets instead of open sets. And in some examples, that actually is kind of the more natural thing to do. Theorem. Let's say let X tau be a topological space. Then, well, the empty set and X are closed because, well, they are mutual complements of each other and both are open. So right away you see something can be both open and closed. 2. Arbitrary intersections of closed sets are closed. 3. Finite unions of closed sets are closed. And so you could actually define a topology to be a collection of things called closed sets, satisfying these 3 properties. And it's equivalent to defining a topological space. The proof is actually kind of really straightforward. What the fuck is that? I don't know what's happening. Maybe it's my pen. Proof. Super weird. These follow by just straightforward applications of De Morgan's laws for unions and intersections and complements. So I could just say, you take some arbitrary collection of subsets, then the complement, let's say, over all alpha of A sub alpha, this is equal to the union of the complements. Likewise, you could take a finite collection, let's say B sub I. This is equal to, so I would make sure the associativity is right. This is equal to the intersection of all the complements. So if my sets A sub alpha and B sub I are closed sets, then these would be open, and these would be open. And we use the corresponding properties for open sets. These are both De Morgan's laws. I don't know if it's a capital D or a lowercase d. So a particular example where this is supernatural, well, okay, this is extremely natural to do, supernatural maybe being something different, is if you ever get interested in something called algebraic geometry later on. Very hot subject, one of the biggest kind of branches of math right now. So this has to do with kind of the geometry of polynomial equations, or as you know, maybe a first intro into it, something called the Zariski topology. Let's just say on R2. Well, if it's on a non-algebraically closed field, it's kind of gross. So maybe we'll just do like C2. Or Cn, doesn't really matter. So I'd say a subset Z of C2 is closed if there exists some polynomial in two variables such that Z is equal to the set of zeros of F. Well, that's one way. In general, you'd say, you know, if there exists, let's say, finitely many, such that equals the intersection of all those. So it ends up being kind of more natural algebraically to speak of closed sets instead of open sets. So open sets in this topology are defined by complements of zero sets of polynomials. Yeah, it's just kind of a weird thing. Something you might see in, I guess, like a 741? I don't know. Somewhere in the mid 7s to 800s class. Yeah. All right, so the next video I'm going to talk a little bit about continuity. Just a little bit.